So in this extra topic, we are going to be looking at we're going to explore the torque speed characteristic of an induction motor in a little bit detail and try to look at other operating regions outside of just a motoring mode alone. Let's go back to our induction motor torque speed characteristic. So this was if this is the slip axis, slip equal to 0 is here, slip equal to 1 is here. This is same as omega mech being 0, and this is same as omega mech being equal to omega synchronous. Okay? And the torque speed characteristic that we got was this particular shape, where this is the holding torque or the startup torque. And this is going to be our maximum torque. And this is where the torque is set at 0. When we are in this region, the motor is going to operate in a stable manner. If we say we are initially at this point, our load torque is, let's say, tau load is here, then the corresponding slip at steady state will be some S1. Now, if we were to increase our load torque, let's say our load torque doubles, and we go to this new point, tau L2. Now, what's going to happen? As soon as the load torque doubles, the electromagnetic torque is not going to double. So we have seen this already happen in a permanent magnet synchronous motor. What happens? The rotor starts to slow down because the added energy. Previously, the motor was supplying tau L1 times omega. Then now it's asking for some omega 1. Now the load torque has suddenly increased, but the speed is still at the same point. So it's going to start to draw more energy because this is greater than this one. So this is drawing more power. So P2 is greater than P1. So we are going to draw more power, but the power is not coming from the electrical system just yet because it takes some time for the current to build up, given all the huge amount of inductances that are in this motor. During that time, the energy is coming from the inertia, half j omega squared. So the energy stored in the inertia starts to go down because you're dragging power out of it. Think of it as a capacitor with some voltage across it. So there is an associated energy, half CV squared. Now you put a resistor across that capacitor without putting any additional energy source into the capacitor. The current being going into the capacitor, basically a charge flowing out of the capacitor, is going to drain the capacitor voltage. Same thing happens here. The energy power going out of this inertial energy is going to drain the speed of the inertia. So if the speed starts to come down, what happens? The slip starts to increase. Because what was the definition of a slip? Slip was equal to our omega mech divided by omega synchronous minus omega mech divided by omega synchronous. So as the mechanical speed starts to come down, our slip starts to increase. So we are starting to go farther out. And we are going to go and settle at a new point, S2. This is a negative feedback effect. As the torque increases, the rotor starts to slow down. And as the rotor starts to slow down, the torque produced also increases. And when the electromagnetic torque matches the demanded load torque, that will be the new stable operating point. So up to this point, we are in the stable operating region, up to the maximum torque, S equal to S max. This is exactly the same as what happened in a permanent magnet synchronous motor. Up to delta equal to 90 degree, it was operating at a stable point. For a given current, our load angle, our load equation, our torque equation was some 3 by 2 times pi RL ns divided by 2 Br magnitude times Is space vector times sine of delta. So for a fixed current, the torque increased as a function of delta. On the left half, when delta was less than 90 degrees, the same thing was happening. When you asked for more torque, the rotor fell behind, in turn creating more torque, which led to a stable equilibrium point where it could operate with the new delta angle. But in case of a synchronous motor, the speed was always synchronous speed. Only the angle between the rotor and the stator magnetic field BMS, stator current induced magnetic field BMS, and the rotor magnetic field BR started to vary for a fixed current. Right? But in case of an induction motor, but the speed itself was a constant in that case. In case of an induction motor, the speed is not a constant. As the slip changes, the mechanical speed itself starts to change. So it always starts to keep falling behind and behind. The rotor starts to keep slowing further and further. It doesn't operate in a synchronous manner. Once it goes to this maximum torque, and let's say you demand more torque, if your load torque is even further higher, then what is going to happen? Since it's asking more torque than it's being produced, it's going to take power out of the inertia, and the speed will start to slow down even further. If the speed goes down even further, slip increases even higher, goes more closer to 1, and it comes to a new operating point. At this point, if you look at the electromagnetic torque, tau em, the deficit is even greater than what it was before. The deficit before was this much. Now the deficit has increased. That means more energy is drawn from the inertia, the speed slows down even further, slip goes down even higher. We go to a new operating point, until we come to a complete stop. So the right half of the motor is stable operating point. The left half of the motor in this case is an unstable operating point. So let's look at the case, what happens. What does it mean when the slip becomes negative? So if you plug it into our equation, our torque was a slip characteristic curve equation that we derived. The negative slip would basically recreate the same waveform all over again. So this is slip equal to 0, and this is slip equal to 1. So what does it mean to have negative slip? That means, going back to our expression here, our mechanical system, just recording. So our mechanical system is rotating faster than the synchronous speed. Right? So if slip is less than 0, that implies omega mech is greater than omega synchronous. We have seen something similar before in case of permanent magnet synchronous motor, where our rotor magnetic field started to lead the stator magnetic field. In that case, it went from motoring mode into a generation mode, where we are converting mechanical energy into electrical energy. Same thing happens here. When the mechanical speed is greater than the synchronous speed, we end up going into generation mode. But the space vectors, the EMF space vector and the rotor current space vector, all of those are still rotating at exactly the same speed as it was before at steady state. All right, so what's happening is, if you look at the rotor frequency, omega r, we said that was slip times the electrical frequency. Now, if slip is negative, let's say slip is minus 0.1, and our omega e, let's say, is 2 pi times 50 hertz, then our electrical frequency is now actually rotating at 2 pi times 0.5 hertz. So the frequency at which the electrical components are going of negative 0.5 hertz. And we have already seen what this negative frequency means, right? So the rotor is rotating faster than the BMS space vector, but we know in induction motor at steady state, all the space vectors have to rotate at the same speed. And how do we do that? So let's think of a case where a train is going at 100 miles per hour, and another train is going parallel to it at 105 miles per hour. Now, if someone inside the train going faster at 105 miles per hour runs in the opposite direction at 5 miles per hour, then they would be exactly at the same speed as the first train. So we had one train that is traveling at 100 miles per hour, and the second train that is going forward at a higher speed, 105 miles per hour, but we have some person inside the train running backwards at 5 miles per hour. Their position with respect to this train would always be a constant. As this keeps going faster and faster, this person is going to go back and back further, so that the tip of this person and the tip of the train on the other side would exactly be matched together. So the same thing happens because the space vector at steady state, rotor EMF space vector, rotor current space vector, the stator space vector, all of them have to be at the same speed. The angles between them can be different, but the speed between them cannot be different at steady state. So the way that happens is, as the rotor is rotating faster than the stator of magnetic field space vector, the currents induced on the rotor are in such a way that they create a space vector that rotates in the opposite direction, similar to the person running in the opposite direction. And we already seen how to create space vectors that are rotating in the opposite direction, basically reversing the phase sequence of the current on the system. When we wanted to rotate a permanent magnet synchronous motor in the opposite direction, what we exactly did was swap out the phase terminals. So exactly the same thing happens here. So on the stator, let's say this is your A phase voltage, A phase current. Let's say this is the B phase current. This is the C phase current for the stator. When you look at the rotor, of course, the frequency is going to be different because it's a much lower frequency. Right? This is going to be a A phase current. And then 120 degrees is going to be a C phase current. And 240 degrees is going to be your B phase current. So the sequence gets wrapped around. Now, if you do the space vector transformation for these currents, you will get a space vector that's rotating in the opposite direction. At what speed? At 0.5 hertz in the opposite direction. And the rotor itself is rotating at, instead of 50 hertz, it's rotating at 15.5 hertz. And then the space vector is rotating in the opposite direction with respect to the rotor at negative 0.5 hertz. So we end up with the total speed at which the space vector rotating is 50 hertz. So this is the same speed at which the BMS space vector and all of those are rotating. So this is what generation mode means in a induction motor, where the rotor sequence component basically flips itself in such a way that the slip ends up becoming negative and the frequency is interpreted as being negative. And this is exactly the same as what we saw in case of permanent synchronous motor, where rotating we change the direction of rotation by just flipping the direction of rotation. Let's look at the case. What will happen if so this part is the motoring mode. This part is generation. And because our speed is still positive, this is omega m axis, let's say. Our speed is still positive, but our torque has become negative. So speed positive, torque positive, motoring mode, tau times omega would have been positive, power going into the mechanical system. Here tau times omega will be negative, power coming out of the mechanical system, so generation mode. Now on this side, as the slip increases further, you can again plug it into the curve that we have, and this is the curve that you will get from there. This part is basically a regeneration mode. So the rotor is rotating in one direction, but you're applying a torque in the opposite direction to basically slow down the motor. So when you have an induction motor connected to a drive, you can have a motor rotate in one direction, but apply a torque in the reverse direction to break the motor in effect, to break the motor quite fastly. So what happens is all the energy stored in the inertia is basically drawn out and given back to our electrical system. So this would be the regeneration operation mode. So let's look at a one-phase induction motor and see how that will behave. So in case of a one-phase induction motor, we already said that the magnetic field in the air gap only pulsates. So this is our theta, and the magnetic field in our air gap for a one-phase motor just pulsates up and down. It does not move in any direction. But mathematically, we could decompose it into two components. One is the forward traveling wave, and the other one is the reverse traveling wave. So we could mathematically decompose a single wave into two components. We did parallels with what we do when we do our experiment for estimating the speed of sound, where we have a standing wave. We have a forward traveling sound wave interacting with a reflected reverse traveling sound wave to create standing waves. Here we do the opposite. We do have a standing wave and we decompose it mathematically into one forward traveling wave and one reverse traveling wave. If you look at just a forward traveling wave alone, this is the same as what we would have gotten for a three-phase motor. Absolutely exactly the same. In case of three-phase motor, the three individual BA, BB, BA, BB, and BC, which had different magnitudes at the same time, interacted to create one single forward traveling wave, which was going in this direction. So when we decompose this into two, we can think of it as one three-phase motor, which is creating forward traveling wave, and another three-phase motor, which is creating a reverse traveling wave. So the three-phase motor that is traveling in the forward direction in our equivalent model will create a torque that looks like this, which we have already derived on the graph on the left there. Now the torque that's generated by the reverse traveling wave would be the exact mirror image along the x equal to y axis. Right? Whatever this curve is, will be the exact opposite of this curve. So let's think about what's actually happening intuitively. Let's look at the case where we are very close to the synchronous speed. We are operating at this point somewhere. If you look at what's happening, the rotor electrical frequency, as the rotor is rotating, so this is our rotor, and the rotor is rotating in this direction. Right? Let's say this omega mech is 92 radians per second. And our BMS space vector, this one, BMS positive sequence, and let's call this BMS the negative sequence. Our positive sequence BMS is rotating along this direction, but a little bit faster, let's say around 94 radians per second. The difference between these two is going to be the EMF seen by these bars, right, which is going to introduce some EMF voltage and at some frequency omega R. And that omega R is going to be quite small. This is going to be the difference between this and this. So it's going to be 2 radians per second. Now the current due to that will be quite large on the rotor. Right? We have ER divided by square root of R prime square plus omega R times LLR prime, the whole square. This impedance term will be very small in this case. So there will be quite a bit of current that flows through, which sets up quite a bit of a large amount of torque here. But when you look at the negative rotating component, BMS negative, so this is due to the BMS positive. Now the BMS negative is rotating in the opposite direction at 94 radians per second. So this is BMS negative. Now if you look at the rotor is rotating in the forward direction and the BMS negative is rotating in the opposite direction. So the net difference in the frequency seen from here to here, in this case it was 94 minus 92, but in this case it's 92 minus now of minus 94. So the rotor frequency, the second case, so this is for the positive rotating component, is 92 minus of minus 94. That comes out to 186 radians per second. So the current introduced on the rotor due to the negative component is going to be ER divided by square root of RR prime square plus omega R LLR prime the whole square. Now this component is extremely large. That means the IR component is going to be very small. So this is going to lead to much reduced torque due to the negative rotating component. So this torque is due to the negative component BMS, and this torque is the BMS due to the positive component. So once the rotor has started rotating in a one-phase motor, the positive component would end up producing more torque than the negative component. But at steady state, when omega equal to 0, when omega mech is initially at 0, both the positive sequence rotating component and the negative sequence rotating component are rotating at the same speed. So this is 94 radians per second, and this would also have been 94 radians per second. 94 minus 0 would have given you 94 radians per second. So the torque produced by both the IR negative and the IR positive would have been the same value. So the torque produced by both of them would have been the same. So they would have been compelling in the opposite direction. So this tries to rotate in the forward direction. This tries to rotate in the negative reverse direction. And they would basically counter each other at steady state, not creating any torque. So what they do in a one-phase induction motor like the ones you have in your fans and stuff is you have a stator winding, just one coil, but then they have another coil 90 degrees away. And if you are able to create a sine wave here for the voltage and phase shift the coil second sine wave by an angle of 90 degree, then you create a two-phase motor which has a rotating magnetic field only in the positive direction or in the negative direction as you have seen before. And that will end up creating a sustained torque just in one direction alone, not the other one. So what they do is, instead of, we don't have two-phase power supply, it is always typically three-phase or one-phase. So how do we get this two-phase power supply? is basically use the same one-phase power supply that we are getting here. So P and N, same P and N here, but instead they put a capacitor in series. So what that effectively does is whatever the voltage here is, it phase shifts it, not precisely by pi by 2, but very close to pi by 2. Close to pi by 2. And that is sufficient enough to get a positive sequence rotating component that is significantly higher than the negative sequence rotating component. If it was not exactly 90 degrees, only BMS positive would exist, BMS negative would not exist. If it is anything less than pi by 2, this would be more strong compared to this. As it gets closer and closer to 0, you wouldn't have any magnetic field again in the air gap. Alright, so if it's phase shifted, you will have stronger magnetic field, BMS positive, with lower effect of BMS negative. Okay, so once you do that, you get a rotating field and the rotor can start rotating because this is the only torque that will be created. But what they do is this makes the motor more expensive because you have to put a second set of coil. So typically what they do is they make this as a very tiny, very thin coil so that it can be cheap, thin wire, and it's made very cheap. And what they do is you need it only to get it started. If it goes either to this side or this side, one of the other torque will take over. It is this on this part, this torque is greater than this value. This torque is greater than this value. All it requires is to push it to either left side or right side. Once it's been pushed to one side, if it's pushed to right side, this torque will take over. If it's pushed to left side, the negative sequence will take over. So all it requires is the initial jolt. Once the jolt comes about, there is a switch that's open so that this coil is not used at all. You can't use this coil continuously because it's a cheap coil that's made to just get it started, and continuously running it will burn out the coil. And the way they open the switch is somewhat ingenious. They have two mechanisms. They look at that there is a thermal switch which heats up and opens up, or there is a centrifugal switch in case of fans. As the rotor starts to rotate, the centrifugal force will open out the switch so that this coil is not utilized. If it comes to a stop, the centrifugal force will go away, so it will close again and then excite the coil. So whenever you have these motors, fan in your homes, and they don't rotate when you turn the switch on, you can take a broomstick and just push on the broomstick. And depending on which direction you push, well, if you push it in this direction, it will rotate in clockwise direction and continue to rotate in clockwise direction. If you push it in the other direction, it will rotate in the anti-clockwise direction and continue to rotate in the anti-clockwise direction. Alright, you're basically doing what this other coil is doing in the equivalent two-phase startup motor that we have. But the way to fix that, typically what will happen is if your fan is not rotating, this capacitor would have blown out. So all you have to do is just replace the capacitor and the fan would work absolutely fine. Alright. With that, we are done. I will try and post some other additional topics as we go forward.